So this is an advanced higher chemistry lesson. We're looking at Unit 1, Physical Chemistry, and the topic we are looking at is part of reaction feasibility. Specifically, what we're going to look at today is entropy and entropy change, which is denoted the symbol S for entropy. So what is entropy? Entropy is a difficult thing to try and explain because it's very abstract. But entropy is a measure of how disordered a chemical or a system is. So it's a measure of how disordered. The more disordered a system or a chemical is, the more entropy it is said to have. And the standard entropy of a chemical is always greater than zero. So you cannot not have entropy. You always must have entropy. That must be greater than zero. And standard entropy, remember, standard conditions denoted by that small circle in the top right-hand side beside the S. That means we're talking about conditions that are 298 Kelvin and at 1 atmosphere of pressure. Entropy is largely affected by temperature, which is why it's really important whenever we're comparing entropies that we do it under standard conditions. Now, going into a little bit more explanation of entropy and why entropy is called disorder and the effect of disorder. What we mean by a disordered chemical or disordered system is one in which the molecules or atoms are free to move about and change position with one another. So the more freedom that the molecules or atoms in a chemical have to move about, we describe that as being disordered. If things are fixed in one location and cannot move, that's what we would describe as being ordered. Disordered is having the freedom to move. And the more ways in which molecules or atoms can move around, the more disorder they have and the higher the entropy they have. Looking at this figure on the right-hand side, which shows temperature versus entropy for a compound, you can see that if we start at 0 Kelvin, which is absolute zero, you have no entropy. You are a completely, perfectly ordered solid where the atoms inside that solid are not able to move. As you increase the temperature, the particles inside the solid, the atoms inside the solid, are slowly able to vibrate, but they are fixed in a location. So that means that the entropy is able to increase a bit, but it's still going to be quite low whenever you're in a solid. Once you reach the melting point for a compound or an element, you get a massive jump in entropy. And that is because you have introduced a whole new level of freedom to the molecules that allows them to move and hence increases the disorder quite considerably. So as you melt a solid, the molecules are no longer fixed in one position, they're now able to move over one another. However, they are still quite well bonded to one another in a liquid. They are moving over one another, so they don't have complete freedom. So yes, you have an increase in entropy upon melting, which increases as you increase the temperature, but it's nowhere near the freedom that you experience as a gas. And so again, if we keep heating up the liquid and take it to its boiling point, you see an even bigger jump in entropy upon boiling. And this is because once something's formed a gas, all the intermolecular bonds tend to be broken, and the compounds exist as single molecules or single atoms that have complete freedom to move in any direction, to rotate, and also to vibrate. And so they have the most freedom to move about, they have the most disorder. And again, as you continue heating a gas, that level of freedom increases and increases and increases. So the general trend that we see is a constant increase in entropy as you heat up a material, and you see big jumps at the melting and boiling points. The reason for that is because upon melting and upon boiling, you're giving molecules and atoms even more freedom to move around, and more freedom to move around means more disorder. So if we increase temperature, particles move more, which means they have an increase in entropy. Solids have less entropy than liquids, which have less entropy than gases. And we always see a very big increase in entropy at melting and boiling points. Now we're going to introduce you to the laws of thermodynamics. If you've done physics, you might have been exposed to some of the laws of thermodynamics, but the laws of thermodynamics basically are related to the ability of things to move and temperature. So the first law of thermodynamics is called the conservation of energy, and it states that energy cannot be created or destroyed. It can only be transferred from one form into another. The second law of thermodynamics states that the total entropy of a reaction system and its surroundings must increase during a spontaneous reaction. So what this means is that whenever a chemical reaction is happening, it's happening inside a reaction vessel, but that reaction vessel obviously has an environment around it. During a reaction, during a process, the overall entropy of the environment and the reaction flask when added together must increase. Now this means that, for example, if your reaction ends up decreasing the entropy, in order for the second law of thermodynamics to be upheld, the surroundings must experience an increase in entropy. If the surroundings experience a decrease in entropy, it must mean that your reaction experiences an even bigger increase in entropy. So overall, whenever you're doing a chemical process, the entropy of your reaction and its surroundings must increase. Disorder always increases. And the third law of entropy states that if you've got a perfect crystal, so a perfect crystal means every molecule is in a very exact location and it's not vibrating, at 0 degrees Kelvin, then we can say that the entropy of that is 0. But only under those conditions can entropy equal 0. Any change to it being a perfect crystal or to the temperature will give a substance entropy. Remember that Kelvin, K, stands for degrees Kelvin, and the way of working out the degrees Kelvin is to take your degrees centigrade and add 273 to it. So absolute 0 Kelvin, is the equivalent of minus 273 centigrade or Celsius. So we're going to look a bit more detail at the second law of thermodynamics. Total entropy must increase. So if we're looking at an exothermic reaction, in an exothermic reaction, we are releasing energy to the surroundings. If you're increasing the temperature of anything, it results in there being an increase in entropy. We saw that when we looked at the graph for melting and boiling. So if you're releasing energy to the surroundings, you experience an increase in entropy. And the second law of thermodynamics states that there must be an increase in entropy always. So that's absolutely fine. Where you have an endothermic reaction, you're taking energy in from your surroundings. So if you're taking energy in from your surroundings, you're causing the temperature to decrease, which is causing a decrease in entropy. We know that overall, we cannot have a decrease in entropy. So there's got to be something compensating for that decrease in entropy. And it means that the reaction must have an increase in entropy. So if you're an endothermic reaction, which is causing the surroundings to cool down and decrease in entropy, you must be experiencing an increase in entropy within the reaction. So that could be the reaction melts or produces a gas, Or it could be that a bigger compound breaks into lots of smaller compounds, because the more molecules you have, the more freedom there is. But that's really important, because entropy must increase. Endothermic reactions, which decrease the entropy of the surroundings, must be compensated for by an increase in entropy of the reaction. But for an exothermic reaction, because the surroundings are always increasing in entropy, it's okay for your reaction to decrease in entropy. So standard entropy, meaning standard conditions, is a term used to describe the entropy of a chemical at 298 degrees Kelvin and at 1 atmosphere of pressure. And whenever we are talking about standard entropy, we're wanting to look at page 17 of the Advanced Higher Data booklet, which gives a list of at least 20 elements and compounds and their standard entropy values. What's meant by the standard entropy is the entropy value per mole of chemical in its standard state. The only chemical that appears twice, there are a couple of chemicals that appear twice on the list. One is carbon, and that is because carbon will have a different entropy whenever it is diamond compared to whenever it's graphite, because there's a different level of order in terms of how the atoms are arranged. But we also have water appearing twice, and that is because there is an entropy associated with water as a liquid and an entropy associated with water as a gas. And because water can exist at 1 atmosphere pressure and at 298 kelvins as both. Elements do have standard entropy values. So remembering when we talked about enthalpy, that elements do not have an enthalpy of formation. Elements do have standard entropy values. The units of entropy are different to the units of enthalpy. Enthalpy is kilojoules per mole. Entropy is joules per Kelvin per mole. So first important difference is that enthalpy is in kilojoules, entropy is in joules. So if we are looking at both, we might need to either turn enthalpy into joules in order to relate enthalpy and entropy together, or convert entropy into kilojoules to make it comparable to enthalpy. The second thing is that we've got this element of Kelvin to the -1, and that is because the temperature always affects entropy, and so the entropy is changed depending on the temperature. So that's reflected in the units. And as I said, data booklet page 17 gives you a list of standard entropy values. So we're going to look now at standard entropy change. So this is going to be the change in entropy for a reaction. And the equation is very similar to the calculation for enthalpy. So the overall standard enthalpy change is equal to the sum of the enthalpies of the products minus the sum of the enthalpies for the reactants. So we're going to look at an example here. We've got sodium chloride. To do this, so we've got 2 sodiums reacting with 1 chlorine to produce 2 sodium chlorides. The only specification for doing this is that your chemicals need to be in their standard states in order for us to use standard entropy values. In this case, sodium is a solid, chlorine is a gas, and sodium chloride is a solid. Now, where we have got expression, entropy change, is equal to the entropy of your products minus the entropy of your reactants. Now remember, if you have stoichiometry, you multiply the standard entropy by the stoichiometry. So when it comes to our products, we're going to have 2 times the entropy of sodium chloride, subtracting for the reactants, the entropy of chlorine plus 2 times the entropy of sodium. And using values from the data booklet, sodium chloride has an entropy of 72, chlorine an entropy of 223, and sodium has 51. And you can clearly see here, chlorine being the only gas has a much higher entropy value than the two solids. Whenever we multiply this out, we get 142 minus 325, which gives us an entropy change that is negative, minus 183 joules per Kelvin per mole. Now, the laws of thermodynamics state that entropy must always increase, but remember that is for a reaction and its surroundings. So you can have a reaction that has a decrease in entropy. That's absolutely fine. All that means is that the surroundings must be experiencing an increase in entropy. You can kind of predict where a reaction will have a negative entropy because you will see two reactants forming one reactant is usually a sign that you might have a negative entropy. And in particular, if your product is a solid, you'll probably experience a negative entropy as well. But do not worry, negative entropy changes are allowed. It's just that overall a system must have a positive entropy change. For a reaction, it's okay to have a negative entropy change. And so this is the final slide. So this is just giving you a list of reactions in which you might expect to have a negative entropy change. So addition reactions, two chemicals forming one is likely to have a negative entropy change. Formation reactions, again, because you're making one product out of two. Precipitation reactions will generally, because you're forming a solid, and polymerization reactions, and that's because you're going from lots of small molecules to one really, really big molecule. So those are your likely reactions to have a negative entropy change. So this topic covered what was entropy. You got an introduction to the laws of thermodynamics. You saw the requirements for entropy and how entropy changes with temperature. You looked at the comparison of entropy to enthalpy, remembering that one is in kilojoules and one is in joules. We saw that entropy is massively affected by temperature. And we also saw how to work out the entropy change for a reaction. Next time, we'll move on to the final topic in reaction feasibility, which is about free energy. And free energy combines enthalpy and entropy to give us one value. So I'll catch you next time.